So students, this is a positive charge Q placed at origin, and this is, I have here at, this is plus Q charge, and there's no force acting on them. So it is at such a far away distance. So I call this distance as infinity when there is no force between these two charges. And now I am bringing this Q charge at a point which is at a distance r. So let this be point P. So this is at a distance r from the origin, from this positive charge Q which is kept at origin. So I am doing the work. So this is, so actually electrostatic force is repelling this plus Q because this is plus charge. So but I am working, so this is the applied force that is applied against the electrostatic force. So this is applied force, and this is electrostatic force. So when you so electrostatic force is conservative force, you know it. So when I'm doing this work against this field force, so work done by me means work done by the external force will be stored in the form of potential energy. But one thing I need to keep in my mind, that I need to move plus Q charge very at infinitesimally small speed. So there is acceleration should not be there. So then only whole means there should be no change in velocity when I am bringing this from infinity to this point. So then my work done will be stored in the form of potential energy. So infinity to this, because here the potential energy is 0. So work done is all the energy, there was no energy over here, so my work done is stored in the form of potential energy. And what is the formula for potential energy? That is equals to K Q by R. So this is the potential energy stored. Now, what is potential at P due to Q? That will be, so this is the, so what you can do is that you can write Q here and Q here. So this will be V. So potential at a point is potential at a point P due to Q is K Q by R. So that's the potential at a point. So this is equals to, it means U by Q. Okay. So it means when Q is equals to plus 1 coulomb, then V is equals to U. Right? V is equals to U by Q. So if Q is 1, then V is equals to U. So when Q is equals to 1 coulomb, then potential at a point is equals to potential energy. Okay. So this is what we did yesterday, and Very simple example. We did example 2.2, example 2.3. Now students, there is very important concept of equipotential surfaces. So equipotential, what are equipotential surfaces? So I'm talking about this potential. So equipotential surface means the surface is equi means equal. So potential is same on the whole surface, equal potential at all points on the surface. So those surfaces are called equipotential surfaces. Means potential is a constant value. So definition is also given in the book. An equipotential surface is surface with a constant value of potential at all points on the surface. And that's the formula. V is equals to K Q by R. So if R is constant, of course this V is constant. So some of the time we have some figures. So these figures are also asked in the exams, that for a single charge Q, what is the shape of the equipotential surface? That's 1 mark question will be there in the exam. So if this is Q, so assume it in 3D space, the surface of sphere will, this is plus Q, so R will be same. So this is sphere, okay? So radius will be same on all these points, and K is 1/4 pi epsilon naught, and Q is the charge. So these two are already constant, and if R is also constant, then value of potential will be the same on all the points of the sphere, and that is why sphere is equipotential surface. So all these spheres are equipotential surfaces. That is figure A in your book. Now we have this plus Q charge. So electric field lines are radial. Okay, they are radial. So that's figure B. Now, so this was the equipotential surface about the charges. Now if you have instead of one, you have two charges. Suppose you have a dipole plus charge and negative charge, or you have two same charges. So these questions are also asked in exams. So you can see this is figure 2.11 and page number 60 in your NCERT. So when this negative positive, obviously you will have a sphere as equipotential surface. Here also you will have sphere as equipotential surface. So here also spheres as equipotential surface, here also spheres as equipotential surfaces. And here in positive and positive charge, so these are the surfaces are, so these are all sphere, okay? Books figure 2.11 clearly there in your book. Now this was about the charges. Now if instead of charges I have electric field, then what will be the position of the equipotential surface? So if there was single charge, then equipotential surfaces are sphere. So even pair of charges. But what if this is the electric field line? Then the equipotential surfaces are in the plane perpendicular to the electric field. So the electric field is, suppose along the x-axis. Then this plane, equipotential plane, will be along the yz axis. So this is yz plane, not axis, yz plane. And if electric field is along y-axis, so this question is asked in the exams, then equipotential surface will be along the xz plane. And if electric field is along z-axis, then equipotential surface is along the xy plane. So these are the questions normally asked in the. Now we have the relation between field and potential. It will be there in your notes. And potential energy of a system of charges. This is also quite easy. So I don't think there will be any problem in deriving it. So I told you that potential energy is the energy stored due to work done by external agency. And the formula also we did that V is equals to U by Q, and U is, if I'm bringing from infinity, then U is work done. So V is work done per unit charge. So U is nothing but the work done by external force, and that is stored in the form of potential energy. So if you are bringing from infinity, there is no charge over here. So you are bringing, suppose Q1 charge from infinity to this point. Now, are you doing any work? There is no charge, there is no field over here. So you are not doing any work actually in terms of physics. Okay. But now you have brought it here, so the potential, now the Q1 is here, so it will have, this point will have a potential that is equals to KQ1. So suppose at point P, this is the potential at point P, is KQ1 due to this Q1 charge, and so this distance R1P. So this distance can be taken as R1P. So V is equals to KQ by R. Now I am bringing another charge from Q2. So the work done on Q2 will be given as K Q1 Q2 divided by R12. So the distance from this point I will be taking this distance. If I brought Q2 here, so this distance R12. So this is the work done on Q2. So what will be the potential energy of the system? So this is the potential energy, because here the work done was 0. When I was bringing Q1, work done was 0. For work done on Q2 charge bringing, because already I have the potential due to Q1, so I have to overcome the repulsive force due to Q1. And now so what is work done? Work done is equals to Q into V. So work done on Q2 and into V1. Now I have these two charges, Q1 and Q2. Now at this point, what will be the potential due to Q1 and Q2? Because again, if I want to do the work on Q3, if I am bringing one more charge, so that will be equals to K, similar in the similar form I can write Q1 Q2 upon R12 plus. So this is the work I have already done. Now what will be the work on in bringing Q3? So similarly, so this was this work I have written over here, and now this will be the work done by Q3. So I'm writing a total work done, suppose. So this is the work done on Q2, and now the work done on Q3 will be written as K Q1 Q3 upon R13 plus K Q2 Q3 upon R23. So initially there was no charge, so work done in bringing Q1 was 0. Now work done in bringing Q2, now Q1 is already there, so work done in bringing Q2 is K Q1 Q2 by R2. Now Q1 and Q2, two charges are already there, and I am bringing Q3. So what will the work done in bringing Q3? So there will be potential here due to Q1, and there will be potential here due to Q2. So this work done on Q3 will be Q3 V1 and Q3 due to V2. Okay. So now that thing is there. So this is, and so work done on Q3 is this. So this I have added, and I get the total work done. So total work done is written in as 2.26 equation in your book. So students, work done is simple, Q into V. Okay. And if only one charge is present over there, so only this much work done. So if two charges are present over there, so I need to overcome the repulsion due to Q1 and overcome the repulsion due to Q3. So this is just like superposition principle I'm using here. So work done in, so Q into V, so when I'm bringing Q3, work done, that will be, so I need to overcome the potential due to first one and then the due to second one, and that will be the formula. So I hope you have understood it, and more will be clear from example 2.4. So we'll understand this more by doing this example. So we have four charges arranged at the corners of a square of side D. Find the work done to put together this arrangement. Okay. So see, first of all, this work done, it doesn't matter which charge you are going to bring first. Okay, because the work done depends on the final arrangement of charges and not on how you have put them together, means. So let us suppose that you have bought plus Q charge to point A. So this is one of the vertex of the square, and you have bought this plus Q charge over here. So what will be the work done? What will be the work done in bringing, work done to bring plus Q to A? So as no charge is present over there, So obviously there is no work done. So the work done is equals to 0. Now work done, you are bringing now minus q charge from infinity to point B. So this is your point B, and this is minus q charge that you have bought, this minus q. So what will be the work done? So that work done to bring minus q to B. So that will be given by, even that is equals to charge at B that you have bought multiplied by electrostatic potential at B due to plus q at A, due to plus q at A. Is this clear? So what is the charge at B? Charge at B is minus q that you have bought, multiply potential at B due to plus q at A. So due to plus q, what is the potential over here? So V is equals to K plus Q divided by R. So R is the distance. So what is the distance between the square? So it is given in the question that the distance is D. So simple. So potential at this point is equals to KQ upon D. So that is equals to K. What is this K equals to? Coulomb's constant, 1 upon 4 pi epsilon naught. This is what K is. So that is equals to K Q upon this R is D. So students, this is very simple, and this will be equals to minus K Q square by D. Now third work. Now I am bringing work done to bring plus Q to C. So this is C point over here, and this is plus at C about plus Q charge. Now this will be equals to charge at C multiplied by, just like charge at B, so charge at C multiplied by potential at C, because work done is equals to Q into V. So V is the, so you are bringing this charge Q, so work done in bringing Q, and you are bringing it to point P, okay, any point. So, and this is the potential at that point. This is the thing. So you are bringing Q to a point, bring Q to a point, okay, and this is the potential at that point that you need to multiply, and potential is a scalar quantity. So you just, so there will be potential at this point due to A and due to B, okay. So work done is equals to Q into V. So Q you are bringing, and V is the potential at that point. So what is the potential at C? So potential at C is due to plus Q charge at A and due to minus Q charge at B. Okay, so this is equals to potential at C due to plus Q at A plus potential at C due to minus Q at, so this was potential at C due to plus Q at A, right, and potential at C due to minus Q at B. So students, this is so simple. The only thing is that work done is in bringing the charge at a point is equals to that charge multiplied by the potential at that point. And potential at that point, we know this formula, that V is equals to KQ by R. Okay, so it is as simple as that. So that is equals to, now charge you have bought is plus Q at C into potential at C due to plus Q at A. So what is the formula for V? So V is equals to K. Now what is this distance? Diagonal of a square. So diagonal of a, this is D, this is D, this is perpendicular. So this is under the root D square plus D square, D square plus D square is 2D square. So under the root 2D is the diagonal of the square. So this distance of potential at C due to A. So here the distance is now under the root 2D. So root 2D is the distance. So K, Q, so this is your Q at A divided by, so potential at this point. So how much is the distance at this point? This is root 2D. So plus Q into root 2D. So KQ upon R. So this is so K into plus Q divided by distance. How much is the distance? Root 2D. Plus, now again, potential at C due to B, and that is given by K into minus Q. So this is due to minus Q. And how much is the distance? Distance is D here. Okay. So this is the work done in bringing plus Q to C. Now fourth, work done. Now I have to brought a D charge minus Q. Okay, at this point D. Now these are all complete vertices of square. So work done to bring minus Q at D. So this will be the work done is equals to minus Q into potential at D due to the charge configuration, due to the charges at A, B, C. So now the potential, so this will be written by superposition principle, right? So now that will be equal to, charge at D multiply by potential at D due to plus Q at A plus potential at D due to minus Q at B plus potential at D due to plus Q at C. Okay. So that will be equals to, so charge at D minus Q into potential at D due to this plus Q. So how much is the distance? Distance is D. So K into plus Q, charge at A divided by D, plus potential at D due to this B. So how much is the distance? Root 2D. So K into minus Q divided by root 2 into D. Then due to plus Q at C, so K into plus Q divided by how much the distance from this plus Q to D? That is again D side of the. So students, it's so simple. Okay, so work done is Q into D, and D is the electrostatic potential at that point, and that will be due to presence of all the charges. So same will be the case of electric field also. Electric field at D point is due to A, due to B, and due to C. But electric field is a vector field, is a vector quantity, so you need to do it vectorly. But here the advantage is that potential is a scalar quantity, so you can simply add them. Now you need to find the total work done. So total work done will be, so this is suppose W1, W2, so this was suppose W2, and this is W3, and this is W4. So total work done is again a scalar quantity, so you can simply add the work done. So that's equals to 0 plus minus KQ square by D. Students, in exam you need not to write this line. You need not to write this line in exam. This is just for your understanding. Okay, I have written. Then W3, that is plus Q into K into plus Q divided by root 2D minus KQ upon D. Okay, and then plus this W4 I will write here. So students, what is common in all of them? K is common, you can clearly see, and D is also common in all the terms. So we have how many terms? 1, 2, 3 and 4, 5, 6. So we have total 6 terms. Okay, see, Q square is here also it is Q, and this is also Q and Q. So this is Q square, Q square. Here also Q is outside, so multiply this Q will all, so Q square is there. So K is with all of them, Q square is with all of them, and D is also with all of them. So what do I have left with this term? This term was 0, so leave it. This term is minus K Q square. So if you want to take minus common, take minus common also. Okay, because a lot of this minus term will whole be taken, so this sign will remain the same. So what do I left with here? Here I am left with only 1. Then plus what am I left with here? So this is KQ square by D. So I am left with only the term 1 by root 2. So but I have taken the sign minus also common, so this term will become negative. Okay, so minus 1 by root 2, and this negative term will become positive. Now I have taken negative term, negative outside common, so these 3 sign will remain the same. So here also I will left with only, what have I left with? Only 1. So plus so 1. What term I left with here? This is minus 1 by root 2. And what these two terms, so same, plus 1. So we can calculate this, and this will be 1 plus 1 plus 1 plus 1, 4. So this is minus k square by d, 4, and this is minus 1 by root 2 and minus 1 by root 2, so minus 2 by root 2. So 2 by root 2 is root 2. So student, this is the work done for this configuration. So you can take a screenshot of it and you can write it later. So it doesn't matter how you have arranged this configuration, but the work done will remain the same. Now there is another part to this question. This part B, that so these were the charges plus Q, minus Q, and minus Q here, and plus Q. Okay, now what you are doing is you are bringing a charge Q naught here at the center of the square. So this is the center. The 4 charges are at the corner, and this is the center of the square. So how much is the extra work needed to bring this Q naught? So obviously the formula will remain the same like here. So work done to bring Q naught at E. So this point is E. So this was point A, B, C and D. These were the points where these charges are placed at 4 vertices of the square. So that this work done will be equal to the charge that you have brought, charge at E, Q naught, into electrostatic potential at E due to plus Q at A, minus Q at B, plus Q at C and minus Q at D. So due to charges plus Q, minus Q, plus Q and minus Q at A, B, C and D, and you have to write here respectively. Okay, so means plus Q charges in respect of A, minus Q at B, plus Q at C and minus Q at D. So potential due to all of them. So that is and you can clearly see here that potential at E due to this plus Q at E, this distance is this was the distance root 2d. So this distance is d by root 2. So all these distances are same now, d by root 2, d by root 2, because diagonals of square bisect perpendicularly. So all these sides are d by root 2. So but here potential due to this plus Q will be K Q by D. So distance is same, d by root 2. Now due to this is negative. So K into minus Q by D by root 2, plus now due to C at charge at C, so K plus Q d by root 2. This is the distance R, and now the V at E due to the charge at D. So that is minus Q upon d by root 2. So students, clearly this will cancel out with this, and this will cancel out with this. So this is 0, so 0 multiplying thing is 0. So because the potential at this point was 0, so potential is a scalar quantity, and this potential due to this is cancelled out, potential due to this, potential due to this cancel out, potential due to this. So there can be 1 mark question in any way. Definitely it will be there in the exams. Okay, so now let us the next. So this was the potential, and next topic is potential energy in an external field. So this was potential energy due to there was no field already there, but now we have a field already there. So potential energy in an external field. So potential energy in an external field. Now, the electric field is not produced by any charge, but this is it might be due to charge configuration. It is already there, and we are bringing the charge in this um, field. Okay, so when there was no field and I was bringing charge q, the work done was 0, but here the work done will not be 0. So now the work done in bringing the charge from infinity, let this be, I'm bringing here plus q charge from infinity to this point, and in the external field, then there will definitely be some potential at this point due to this electric field. So this V is due to the electric field already there. So electric field at this point, I can write it at, so this is point P, so there are two ways. So electric field at P or electric field at this position. So the position vector R from this some origin, and this is the location of this point. So VR. So potential energy of Q at R so potential energy of Q at this position R in an external field E is equals to Q into V. So same formula, QV, potential energy, U is equals to QV. So the work done is also QV. Okay. Now this was the potential energy of a single charge. Now I am bringing one more charge. So I'm bringing suppose Q2. So this was suppose Q1, and so this was suppose Q1 I was bringing at position R1. So this will become R1. This will become R1. Now I'm bringing Q2 at R2. So this will also be the work done in bringing that charge, that is potential energy, work done, same. Now the work done, so this was the work done on Q1. Now the work done on Q2, so the work done on Q2 will be equals to, same formula students, Q2 into the potential at that point, at that location. So now what is the potential at that location? So potential at that location was due to the field, first thing, that was VR2, due to the field already there, plus due to the potential due to Q1, Okay, so this is, suppose I have bought here the charge Q2. So potential at this point Q2 will be due to Q1 and due to electric field. So this is due to electric field, and so whether you write it again or not, it doesn't matter. So students, this is the potential due to electric field, okay, at R2. So this is due to E. So that was due to E. But now potential is due to Q1 also at this point. So what is potential due to Q1? KQ by R. So K, Q1, and what is the distance between them? So distance between them is R12. Okay, so simple. Okay, students. So now we have this is the work done on Q2. So what is the total work done? So total work done is stored in the form of potential energy, and that is equals to Q1. So this was Q1. V. So QV. So Q1 and V was due to the electric field at that point, at that position, plus Q2. Now this is the work done on Q2. So Q R2 due to electric field, this potential due to electric field, plus Q, this potential due to the, so K Q2 Q1 Q2 upon R12. Okay, so this is the potential energy of the system in electric field. So we started our topic with the potential energy. So this was also same, right? So students, there was no charge in the beginning, so potential was 0 at that point where I bought Q1. Now I have bought Q2. So Q2 I have bought, so there was potential due to Q1. So this is the potential due to Q1 into Q2. Now I have bought Q3. So potential due to Q1 and potential due to Q2. Okay. So both I have multiplied with Q3. So students, this is all the same thing that we are doing. Simple thing is that only two things we have done. That is, the work done is the potential energy is equals to Q into V. And what is this V? This V is the potential at that point. So you are bringing Q to R, this position. You have bought this Q to position R. So how much the work done is the potential energy stored. So Q that you are bringing to this position multiplied by the potential at this position, and this potential is due to all the charges, and due to all the charges, so the formula will be V is equals to K, whatever the charge is already over there, suppose capital Q or whatever be the charges, or due to electric field, so this V is due to at that position due to the electric field also. Now, do you know the formula between electric field and V? Okay, let us see. See, I told you that we have these four formulas: Coulomb's force, K, Q by R square. Then we have electric field due to Q, KQ by R square. Then we have, so instead of R square, now I will have R. So potential energy, let us write potential energy first. KQ by R, and then V is equals to KQ by R. So these are the four basic formulas. Okay, and you can write this formula as this is equals to F is equals to Q into E. And similarly, you can write from here these two formulas. U is equals to Q into V, right? And now you have one formula from E and V, okay? From the, so this is 1, this is 2, this is 3, and this is 4. So this was due from 1 and 2, this formula is from 3 and 4, and now we have formula from 2 and 4. So what is that? So simply you can see that E is equals to KQR into R. So this K into R is V. So E is equals to V by R. Or you can say V is equals to ER. So that's the relation between E and D. So this formula will be this formula. So V due to E is equals to E electric field into the distance, this R. Okay. Now let us do one example and you will have more clear understanding. Position or distance, anything you can take here. So this thing. Now this example will make the things more clear. So example 2.5. Determine the electrostatic potential energy of a system consisting of two charges, 7 microcoulomb and -2 microcoulomb, and with no external field. So external field is 0. Placed at, so this charge is placed at -900, and this charge is placed at 9. So this is in centimeters, okay? So in centimeters. So you can clearly see X, Y, Z coordinates. So these two charges are along the x-axis only, okay? So this origin, this is -9, this is +9, because Y and Z coordinates are 0, okay? So you need to find the electrostatic potential energy of the system. So simple. So electrostatic potential energy will be given by K, because there are only two charges. So this is the formula that you have. U is equals to KQQ by R. So K, what is your this Q? So you can write it as K Q1 Q2 by R. K is 9 into 10 raised to the power 9 into what is Q1? So Q1 is 7 into 10 raised to the power. So micro means 10 raised to the power -6, and then -2 into 10 raised to the power -6 divided by the distance between them, and this is 9 centimeter, 9 centimeters. So total distance will among them will be 18 centimeter, and 18 centimeter can be written as 0.8 meters. So this is the distance, 0.8 meters, and this will comes out to be -0.7 joule. Okay, so this was the first part. Second part of the question, that how much work is required to separate the two charges infinitely away from each other. So work done in separating. So obviously that is equals to the work done in making this system, work done in bringing Q1 and Q2 together, right? So work done in separating them, separating Q1 and Q2 will be work done in bringing Q1 and Q2 together. So how much is the work done that you have done in bringing? This is the work done that you have bringing. So this is the work done in bringing, potentially of the configuration, work done in bringing Q1 and Q2 together. So obviously this is negative work, so this will be positive. So separating them, the work done will be positive. So this is the work done in separating them will be given by, or you can write it, the way how you will write it is that U2 minus, you want U2 minus U1. So this is U1, you can also write it as U1. You want to separate them, so there will be no final potential energy of the system when you will separate them. So final will be 0 and initial was minus 0.7. So that will be equals to 0.7 joule. So this much is the work that you have to, this much will be the work in separating them. Okay, next part of this question, C part. So student, this is the last part of today's lecture, and this is very important. Suppose the same system is now placed in an external field. So the system is same, but we have placed it in external field, and that external field is given by, the magnitude of the field is given by A into 1 upon r square, and A is constant. So value of A is 9 into 10 to the power 5 coulomb per meter square. So what would be the electrostatic energy of the configuration? So this is what we need to find. What will be the electrostatic energy? So this is the same, that this relation that we have derived, this one, same, this we are going to apply. So obviously the energy due to these two charges will of course be there, and if you write that formula of U, that was so in bringing Q1, how much is the work you did? In bringing, see, work done is equals to U is equals to Q into V. So you are bringing V at this position R. So already the potential at that point. So you are bringing Q to R. So this is the work done that you need to. So simple. And this potential can be due to two things. One is due to, if there is any electric field, then due to electric field, or due to some already charge present over there. Suppose Q charge already present, so due to Q. So due to Q, V is equals to KQ by R. And due to, if it is E, then we just did that formula that V is equals to ER. So then V is equals to ER. So students, this is the only thing. So now first of all you are bringing Q. So Q, due to potential there due to the field at R1, plus now potential, now you are bringing Q2, right? So potential due to the, at that point Q2 due to, so this is due to E, this is also due to E, and now Q1 is already present over there, so you are bringing Q2. So Q2 into potential due to Q1. So that is potential due to Q1 will be K Q1 upon the distance, that is R1, 2. So simple, students. So that's equals to, so what is the this field? So A into this we have already calculated, right? This we have already calculated, this thing. So this we already know. This value is minus 0.7 joules. Okay. So now what will be this? So Q1 is 7 microcoulomb, and So this is Q1 into VR1, so this is A into, so electric field is given to us, that is, this is the electric field. And this electric field, as I told you, that the V is equals to ER. So this formula will be V is equals to ER. So this V is equals to ER. So Q1 into E. What is E? A upon R square into D is R. Okay. So this one R will be cancelled out. Okay. So this will be Q1 A upon R. Right. And so students, you have one more plus point today. I am recording this lecture, so you will also find this, I will upload this lecture on the YouTube also after this lecture, so you can watch it again at any time. So plus, similarly you will write this also. So Q2 into, now this is A upon R square is the electric field into the distance. So the distance here is, if it is it was R1 over here, so it is R2 over here. Okay, and R1 and R2, so this distance is your, suppose, R1 from O, and this is your R2. So R1 and R2 are same. That is 0.9 meter and 0.9 meter. So R1 and R2 are same, 0.9 and 0.9. So this was actually your R1 and this is your R2. So V is equals to E into the distance. That is V. This is what you are writing. And this is again same. We have calculated it, minus 0.7 joules. So now this will comes out to be, Q1 is your, what is the value of A? A is also given to you, that is, A is 9 into 10 raised to the power 5. So put the value of this, Q1, A into Q1 is your, so how much is Q1? Q1 is, you have taken as 7 microcoulomb and Q2 as minus 2 microcoulomb. So this is 7 microcoulomb. So 7 into 10 to the power minus 6 into this divided by R is 0.09 plus Q2 is minus 2 into 10 to the power minus 6 into A is 9 into 10 to the power 5, and this R2 will of course we cancel out, only one R2 will left at the bottom, and this R2 is equals to 0.09 plus, or you can write minus 0.7, and this will comes out to be, students, this will comes out to be 9, this will comes out to be 7 T, this will comes out to be 20, this is minus 0.7, this will comes out to be 49.3 joules. So students, I hope you have understood today's lecture, and I will also upload it on the YouTube. So thank you so much for attending this lecture. So whenever, okay, thank you so much.